This paper challenges representational optimism, the assumption that better performance from scaling AI automatically leads to better internal understanding. It proposes the fractured entangled representation, FER, hypothesis, suggesting that standard training creates disorganized internal knowledge. FER is like spaghetti code, concepts are fractured into redundant pieces and entangled with unrelated functions. This is contrasted with the ideal UFAR, which is organized and modular like clean code. The authors argue that FER could be a primary reason why models struggle with generalization, creativity, and continual learning. To investigate internal representations, the researchers use a tool called a compositional pattern producing network, or CPPN. It functions by taking the coordinates of a pixel as input and calculating that pixel's color as its output. By doing this for every pixel, it generates a complete image. This image isn't just a single output, it's a map of the network's entire behavior. The key advantage of CPNs is that the activity of every hidden neuron can also be visualized as an image. This unique property allows for a complete, intuitive view of how the network internally constructs its final output. One set of examples comes from PipReader, a website where users spread images. Instead of training a network to meet a specific goal, PipReader used an evolutionary algorithm where humans provided the fitness signal simply by picking images they liked. This process is open-ended because there is no final objective. It encourages exploration and allows for serendipity, where an unexpected discovery can become a new path to follow. The paper highlights that this exploratory method consistently produced CPNs with clean, modular internal structures, the kind of organization they define as a unified factored representation. A unified factored representation, or UFAR, is the paper's ideal for how a network should organize knowledge. It's unified because concepts are stored once, and factored because different concepts are kept separate. The skull image from PipReader is the primary example. Its internal visualizations show that symmetry is learned early and reused. Different parts like the eyes
and mouth are handled by distinct neurons. This good structure is most evident when single weights are adjusted. Doing so produces coherent, meaningful changes to the image, demonstrating a deeper understanding of its components and providing creative potential.
A fractured entangled representation, or FER, is the opposite of the ideal. The paper demonstrates this by training a standard network with SGED to perfectly replicate the PipReader skull. Although the final image is identical, its internal structure is a chaotic mess. The network never learns the concept of symmetry. It computes the left and right halves of the skull as separate, unrelated problems. The authors call this an imposter because it mimics the correct output without any real understanding. This is proven when its weights are adjusted, causing the image to collapse into meaningless noise, unlike the clean changes seen in the UFAR network. The skull is a simple metaphor for a larger problem the authors call imposter intelligence. This is when a complex model appears capable on the surface, but is internally powered by a brittle collection of heuristics. The paper provides real-world examples of this. Past language models failed at arithmetic depending on the type of object being counted. More recent models can perform a task with numbers, but fail the identical task with words. Figure 7 shows an image model that can add an extra thumb to a human hand, but not an ape's hand. These are signs of FER, where knowledge is not generalized, but is fractured into context-specific pockets. So, why do these different representations form? The paper suggests the learning path is critical. The PipReader skull inherited its clean, symmetrical structure from an ancestor that had already discovered symmetry. In contrast, standard SGD training is a greedy, direct path to the objective, which favors messy shortcuts over foundational understanding. This is why open-ended search is so effective. It finds useful stepping stones that can be built upon later. The paper is skeptical that just adding more data is a solution, as it might just create a more comprehensive set of fractured heuristics, especially at the frontiers of knowledge where data is sparse. To summarize, this paper challenges the core belief that bigger models are always better on the inside. It introduces the key concepts of UFAR, the ideal organized representation, and FER, the messy and fractured representation that may be common in today's systems. The visual experiments with CPNs show that the learning process itself, open-ended exploration versus direct optimization, is the critical factor that determines which type of representation emerges, even when the final outputs are identical. The authors connect this to real-world models, suggesting FER may be a root cause for ongoing issues with generalization and creativity, and call for new training approaches.